Hello, and welcome to today's Lunch and Learn. I am Curl Access Services Librarian Bob Exarin, and I am joined today by the incomparable Jon Bachman, who will be talking to us about the geologies of Mars and Earth. Without further ado, Jon, take it away.
Well, Bobak, thank you very much. Mars, I can remember when I was a kid. Oh, by the way, I'd like to thank the people at the Central Regional Rappahannock Library Services for giving me an opportunity to blab like this and to share some information that I hope you find interesting. Ever since I was a kid, I had a little telescope when I was a kid, like one of those little, back in the 50s, it was the Gilbert Scientific Telescope, anyway. And I was blown away by seeing planets. Now, I didn't look at Mars, but I do. I mean, I could find it, but I didn't see it as a whole. But looking at through a telescope when you're a child is a magical moment. And I think that really stirred me as one of the steps toward appreciating astronomy and, of course, our planetary companions and Mars in particular, right? Today, though, I'm going to, as a person who is actively involved in geology and paleontology, I find the geology of Mars just intriguing. And I hope that this presentation adds a little bit of information for you and stimulates your curiosity that you can go on and maybe do a little private research, on your own about Mars, since there's a lot of talk about Mars these days. Mars and Earth side by side. Next slide, please. While both Mars and the Moon are potential targets for future space exploration and colonization, Mars is often prioritized due to its potential for long-term self-sustaining human settlements. Its more Earth-like environments, including a thin atmosphere and water resources, and its potential to answer fundamental questions about the origins of life. Next slide. Well, people are drawn to exploring planets by a fundamental human curiosity to understand our place in the universe, search for signs of life beyond Earth, and push the boundaries of scientific and technological advancement. Slowly, the challenges of travel in space have become solved. Voyages to Mars will propose new challenges, though. The most difficult problems with a voyage to Mars will be getting there, living there, and getting back. Mars is the fourth planet in the solar system, following Mercury, Venus, and Earth, and is about 141.6 million miles from the sun. 141 million miles from the sun. Located in the inner solar system, Mars takes 687 Earth days to complete one orbit around the sun. With plans now underway to land humans on Mars, it becomes essential, I think, that we know as much as we can about this fourth planet, its geology and environment. So, hey, let's take a look at the planets side by side. Mars's planetary evolution has been very different from Earth's. Earth's geological history spans approximately 4.6 billion years, marked by major events like the formation of the planet, continents, oceans, and the evolution of life. Now, Mars's geological history spans roughly the same amount of time as Earth's. The planet has been marked by periods of intense geological activity including something called the heavy meteor bombardment and volcanism. And we know now the presence of liquid water. Over the last 3.5 billion years, though, Mars has lost the two most essential requirements for life: an oxygen-rich atmosphere and a planetary water cycle. So I think we should refer to Mars basically as a hard luck planet. Let's take a look at that. Well, most of the problems with Mars and comparison with Mars has to do with its size. Take a look at the rough comparison there. Earth to the left and Mars on the right. It's about a relative size of the planets. Next. So it's roughly 53%, about half the size of Earth. And about 6.5 Mars could fit inside the Earth. So that's really important to remember, guys. That all of this material about Mars and the geology and the atmosphere and the presence of water and things like that, all of this has to do directly with its size. And we'll explain it, or I'll explain it next. Because of its size, Mars's mass is about 10 times less than the Earth's. Well, this lowered amount of mass affects the force of gravity. And gravity on Mars is 38% of Earth's gravity. A third of Earth's gravity. So a 100-pound person, you guys can figure this out on your own right now. So, but example, a 100-pound person on Earth would weigh 38 pounds on Mars. A planet's mass is a major factor in its ability to retain an atmosphere. Larger planets have stronger gravity, which helps them hold onto more gas molecules, leading to thicker atmospheres. Smaller planets like Mars struggle to retain atmospheres due to weaker gravity and higher escape velocities. This makes them more susceptible to losing gases into space. And that's kind of, I want you to remember that planets slough off gas. The atmosphere that we have here on Earth is slightly giving up slight bits of it every day. Now, we're replenishing it in some respects, but the idea of gravity and mass and the ability to hold an atmosphere is very, very important, especially as we look at comparing Mars and Earth. Mars' early atmosphere was significantly different from today. Okay, denser and possibly richer in carbon dioxide and hydrogen, the Martian climate may have been warm enough to support water on its surface. A thicker carbon dioxide-rich atmosphere would have trapped more heat from the sun, leading to warmer surface temperatures than on Mars today. It is now thought that Mars lost most of its atmosphere about a little over 4 billion years ago. At approximately the same time, Mars is thought to have lost its magnetic field due to the shutdown of the planet's dynamo. Now, this is maybe new information for many of you. So key elements there is loss of a magnetic field and something called a planet's dynamo. Okay. A planet dynamo is a natural electromagnetic generator within a planet's interior that generates a magnetic field. Now, basically, this is Yeah, it's like a giant generator or battery. The electromagnetic generator is the core of the planet. And one of the things about the that we're going to learn about it's Mars's ability to hold gases in an atmosphere is a magnetic field. Well, this is going to come into question as we're going to learn that Mars's magnetic field has seriously been depleted. A planetary dynamo works through a process called electromagnetic induction, where the movement of an electrical conductive fluid, and in this case, it's the core, right? The iron nickel planetary core, which generates an electric current, which in turn creates the magnetic field. Now, the core itself, like for instance, the Earth's core. The Earth's core is a nickel iron, extremely hot. The pressures are unimaginable, but it's also in motion. And our core moves. And as it moves, our core generates an electric current. Okay. And as that current then produces a magnetic field, right? We have aurora borealis and things. We can see the results of a magnetic field. Mars, on the other hand, has a core, but remember, it's only about what? About half the size of Earth, or a third. Next slide, please. Mars's planetary magnetic field offered crucial protection, see, to its environment and potential habitability by shielding it from harmful solar and cosmic radiation, and by preventing the loss of its atmosphere due to the solar wind. Now, next slide. Yeah. Larger planets with stronger magnetic fields like Earth are more likely to retain atmospheres and to support life. This is extremely important, guys, because one of the things people have been obsessed with for many years is the probability that there's life on Mars. Well, we're starting out with a bunch of strikes against us. It says larger planets with stronger magnetic fields like Earth are more likely to retain atmospheres and support life. Okay, magnetic fields, got it, cores, right, okay. Due to the planet's smaller size, there we go, Mars's iron core cooled and then solidified. And the planetary internal magnetic convection process that I've called the dynamo stopped. Next. And that's simply a slide that shows a reduced magnetic field as an example of a reduced magnetic field around the planet Mars. Well, because of that, because of the magnetic field, and because of the solar wind stripping away the atmosphere, Mars lost its atmosphere. Now, I know there's some people that are saying, wait a minute. Mars has an atmosphere. Yes, it does. It has a 1% carbon dioxide atmosphere. Don't take any deep breaths on Mars, okay? Mars does not have, in effect, an atmosphere. Planetary internal convection currents also affect atmospheric circulation patterns and influence climate, weather, and surface features. Okay, that chart there shows convection currents that are coming up from the heated inner core of the inner core planets like Mars and Earth. There are on our planet we have these huge convection currents that swirl and bring up heat from the core of our planet, and then in our case that heat which then disseminates into the crust. It just occurred to me, I wanted to make sure that the crust of a planet can be compared to an eggshell on an egg. Okay. I know, excuse me. I know that it looks like it's that green stuff there looks like pretty thick, but the crust of a planet is very thin. And it's the convection currents that drive what we now know are the plates, Plates, and tectonic plates across the surface of the Earth. We're going to talk about that on Mars in a minute. Next slide. Well, the hard luck continued. A planetary collision known as the Borealis impact 4.1 billion years ago may have also altered the motion of the magnetic field. And you'll remember it's the magnetic field as a key component on retaining an atmosphere. And this giant, it was probably a protoplanet. 4.1 billion years ago is at the very onset of the solar evolution, the planetary evolution of our solar system. And so there was a lot of stuff flying around, and some of it was immense. And this Borealis impact may have been a planetoid that smashed in, as the solar system accreted into its system of planets and that we now know. There were other ones out there. In fact, the asteroid belt, which sits between Mars and Jupiter, probably was a planetoid, or at least a number of planetoids that never coalesced into a larger planet, or are fragments of another larger planet that simply broke apart billions of years ago and stayed in orbit. Next slide. It is believed that the Borealis impact transformed the crust of Mars, altering, there it is, it says planetary dynamo is really important. So the Borealis impact plus the size of Mars and the loss of the atmosphere and the cooling and solidifying of the planet's core all are contributing to some fundamental differences between Mars and Earth. The impact likely increased mantle melting, altering Mars's global heat flow, and potentially contributed to hemispheric asymmetry. Now, I'll explain that in a minute. While the impact may not have directly caused the dynamo shutdown, it played a role in shaping the planet's diminishing magnetic field again. Now, look at the map of Mars there. In fact, that blue area is called the Borealis Basin. That is the area where the suspected protoplanet impacted over 4 billion years ago and deformed, melted, and moved around huge portions of the mantle, if not the entire mantle of the planet, since it's in motion too. So this impact that occurred, you can see the results on looking at the map. With a decreased planetary magnetic field, right, Mars was more vulnerable to solar wind, which gradually stripped away the remaining atmosphere. And Mars became a dead and barren world. Mars's surface is characterized by ancient, heavily cratered highlands in the south, right, and younger, lower volcanic plains in the north. Now, those lowland plains in the north, on this map of Mars, again, is directly a result from the Borealis impact. But you can see that Mars basically has a dichotomy of personality here. There's a southern and a northern part, and the northern hemispheric part of Mars directly was impacted by that impact. Earth's surface is a dynamic and diverse environment composed of land and water, constantly shaped by geological processes and interactions with the atmosphere. Approximately 70% of Earth's surface is covered by liquid water in the form of oceans, lakes, and rivers. Now, astrogeologists now know that Mars had water. Mars has no liquid water on its surface, but there is evidence of past water, including ancient riverbeds and polar ice caps. Geologists have identified the mineral hematite on the Martian surface, suggesting the existence of past water environments. Hematite concretions. Now, a concretion is a small, generally ovoid or rounded artifact that has been created by layers of materials that have been deposited by either water or by wind, and they are rolled into or shaped by natural forces into rounded. These are called blueberries, and the blueberries on the left there on Earth, you can go to rock shops or rock shows, where they sell mineral samples and stuff like that, and you can buy those. Those are little. Now they're called by a bunch of things, but geologists have come to know them as blueberries, and they were found on Mars. Picture on the right there, concretions, blueberries, hematite, probably they're on Mars. So how do these, I had to put this in, how do these blueberries form? Well, water flows through porous sedimentary rock from ancient lakes or subsurfaces. Okay. And as the water percolates, meaning kind of bubbles down, it dissolves minerals, including iron-bearing compounds. When the water reaches areas with different conditions, like a lower temperature or changes in salinity, these dissolved minerals precipitate out of solution, often concentrically around existing grains or particles, forming a spherical shaped blueberry. Evidence of both liquid and frozen water have been found on Mars. Additionally, vast underground reservoirs of liquid water have been discovered deep within the Martian crust. Seismic data from the InSight lander indicated that cracks and pores in rocks deep below the surface are filled with liquid water. The potential reservoir of liquid water is located within the mid-crust of Mars. Well, ready? Specifically between the depths approximately of 11.5 and 12 miles below the surface. Okay, so 12 miles down, there may be reservoirs of liquid water. And apparently the InSight lander detected them. Water may mean some form of life. However, evidence and reality are often very different. Geological evidence now indicates that Mars was once a warm and wet planet. Earth's surface temperatures range from very cold in the polar regions to hot in equatorial regions, with an average temperature of globally of about 59 degrees Fahrenheit. Mars is much colder than Earth, with average surface temperatures around minus 76 degrees Fahrenheit or 76 degrees below zero. And that's during the warm part. Earth's surface is characterized by continents and mountains, valleys, plate tectonics, which create dynamic landscapes and geological activity. Mars' surface is characterized by bare rock, dust, craters with large canyons, volcanoes, and yes, polar ice caps. While no definitive evidence of life on Mars exists, The possibility remains, particularly for microbial life in subsurface environments or ancient environments, like a place called the Jezero crater, where NASA's Perseverance rover is now searching for life, signs of past life. To date, there is no conclusive proof of past or present life on Mars. In other words, after 4 billion years of radiation on Mars, the chances of finding definitive chemical signs of life, at least at the surface, may be minuscule. Even if life existed, the planet's harsh conditions, low gravity, toxic soil, low light levels, and lack of magnetic field pose significant challenges for establishing a human colony. While a definitive date for humans living permanently on Mars is uncertain, NASA's current goal is to send astronauts to Mars for exploration in the 2030s, with a potential first crewed landing by about 2040. SpaceX, under Elon Musk, has also expressed ambitions for Mars's colonization, aiming to establish a self-sustaining civilization on the planet. Exploring Mars helps scientists learn about momentous shifts in climate that can fundamentally alter planets. Mars is there, waiting to be reached. We will travel to Mars even as folks on Earth are still ripping open potato chip bags with their teeth. And that's it.
Well, thank you again, Jon, for saying all of that. I know it was a tremendous amount of information.
I know. It's a lot to grasp, it really is.
For our audience, if you have questions for our speaker today, which I imagine some of you might, given our topic, please leave them in the comments, and we will do our best to get them to Jon so you can hopefully get an answer.
Sure.
And in the meantime, again, I want to thank you. A round of applause for presenting.
Hey. Well, it's always a pleasure to work with the library staff, and in this case, Babak, with you also. I appreciate it.
Well, thank you. And I thank all of you for coming and listening. As a heads up, we will not be having a Lunch and Learn next week, but join us on Friday, June the 6th, as we preview all the summer events and programs happening here at the library.
Out of sight. That's great. Okay.
Thank you again.
Have a great day.
You.